Okay, good morning everyone. Welcome back from spring break. Hope you're all relaxed. As much as students enjoy spring break, professors like it too. I didn't show up till 9 o'clock every morning. It's amazing. So today we're, just a note, for those of you who were not here on Friday, the day before spring break, we did cover lecture 12 because that was, it was anticipated that it would be a lower attendance, and that's an easier concept to go through. So just so everyone's aware, we did go through lecture 12 on Friday in case you weren't there. We also had some technical difficulties that day, so that day was actually not recorded. So sorry about that, but the lectures, the full notes, the ones not with my handwritten notes in there, the full notes with everything we went through in class is on Carmen's been up there for a while too. So if you have any questions about that content is online. But today we're going to go through PID control. This is, if you were to, I don't know the exact numbers on this, but I'm going to guess somewhere around, of all the controllers that are out there in the world, somewhere around 90% of them are probably PID-based controllers. Okay, it's the, we'll get into what P, I, and D mean in a second, but many of you probably heard this before, either from freshman engineering or just me talking about it in class. But we have proportional, integral, derivative control. All right. And so we're going to go through this, and I think one of the reasons why PID control is so popular is that once you start to learn the rules, how you adjust the gains to get favorable behavior is actually quite intuitive. Okay, so it doesn't actually, we'll talk about some caveats to this, but it doesn't really require any knowledge of Laplace transforms and all these other things that require basically going through an undergraduate curriculum like you are all in right now. And so it's intuitive in that they can have people with technical backgrounds, like going through trade schools, etc., learn how to use PID control and get favorable responses based on that, right? And so we're going to go through some of the basics of PID control. I have a system up here that's going to demonstrate some examples of changing PID control gains. And by gains, I mean the proportional, integral, or derivative constant that adjusts how much weight we apply for each term here, and show some demonstrations of the results on the system up front as well. Okay. So we've been talking about proportional control thus far. And just to remind everyone of the context in which we talked about proportional control, we talked about a simple mass spring damper. We'll talk about how the system up front a little bit is a mass spring damper system as well. But simple mass spring damper, you have a mass, we have some ability to force the mass. That means we have, usually we're talking about motors, we could be talking about hydraulic systems, pneumatic systems, etc., many other ways to force something. But we have some sort of way to deliver a force to this mass, and it has natural spring action and natural damping in the system. And this is following off on a lot of the notes we went through already, but we said that for this system, we established, I forgot how my notes went over. Okay, so from previous lectures, we established that if we have a feedback control system and we have a proportional controller, and so if we design G1 to be simply equal to Kp, and so that means that the input to my system is just then Kp times the air signal, then we get the following response. We're going to get a step response if we input a step into the reference, so we're saying that we want our positioning system, our mass spring damper system, at time is equal to 0. We're telling the desired position to go from 0 to some sort of position A. We're going to get a response that looks like our standard time domain response for a second order underdamped system. And then we established some relationships here in previous lectures, right? So we established that we can say the C final for the step response is given by this equation, overshoot by this equation. Sorry, this is a carryover from previous notes, damp natural frequency, etc. And so just recapping from previous lectures, we said that if Kp goes up, so by Kp going up, that means we're making the system more aggressive, right? So we're saying that for a given unit of air, we are responding with more input than if we had a smaller Kp, right? So increasing Kp, you think of as a more aggressive controller. So if we make the system more aggressive, we said that C final will go to A, but only as Kp goes to infinity. So you can imagine having an infinite gain for a small air is a bad thing, but we'll talk about kind of this balance here. But as we increase Kp, C final will get closer to A, which is good, right? We say if we have a desired position of A, that means our actual position will get closer to that, which is a favorable thing. But this also means that we need a really large Kp for this actually to reach A. We said that overshoot is going to go up, which is a bad thing. So, bad thing. Damp natural frequency is going to go up, not really a concern often. Rise time, go down. That's usually considered a good thing. That means our system is faster, so we can respond to faster changing inputs better. Peak time goes down, seen as a good thing. And then the settling time is not going to change at all. So we're indifferent on that one. Okay. And this was a discussion from before spring break, right? We went through these different relationships. Okay. And so some questions that came from class when we talked about this is, okay, we have some good things, right? For instance, rise time going down, peak time going down, and the C final going to A, that was all seen as good, but we have some negative things as well, in particular the overshoot going up. That was seen as unfavorable, so the question is, what can we do about that, right? And spoiler alert is that people have figured out how to improve upon this before, right? So the first thing we're going to talk about in terms of improvements upon this is proportional derivative control. So proportional derivative control, as the name suggests, means that instead of just having a single mapping or gain from the air to the input, which previously we said is just a proportional gain, Kp. All right, so this is just proportional control. I'm drawing this down for a purpose. You'll see in a second. This would be just proportional control. But if we wanted to add proportional derivative control, we're adding extra dynamics in this system. So instead of this being just feeding directly into the current running to the system, we're going to add the influence of the proportional gain times then a derivative gain and then a derivative in the frequency domain, which is just multiplying by S. So now this complete system here is going to be my new controller, or what we call the transfer function G1 of S. Okay. So in terms of in the time domain, we would say that then I of t or U of t, say this is given the specific example. For this example, more generically, we call this U of S, right? So it doesn't matter here. We just said that the input is current, so we'll call it I. But we would say then that I of t, in this example, would be equal to Kp E of t plus Kd d dt of the air signal. Okay, so just kind of put this in context of what would have to happen. We'll talk about the system in a second, but we talked about how we kind of have these divide in feedback control systems where we have the virtual world on this side, usually living in a computer or microcontroller. And then we have the physical world on this side, which is your plant, right? So we're trying to control something that's physical here. So that means inside the computer, at every single time step that this computer is running, before all we had to do was just take the air signal and multiply it by a constant, which, whatever programming language you're comfortable in, you've done things like this all the time, right? Multiplying something by a constant. Now we have to take the derivative of that signal at every time step and multiply it by a constant as well. So it's an extra operation, but perfectly doable as well. Right? So just kind of give you a sense of what would have to happen inside your command line or your line that says output the input. You'd have to have a derivative function on that signal as well. Any questions about that basic idea before we get into why this works and why it's favorable? So in the frequency domain, if we look at this, if we're trying to come up with if we were to merge and condense a set of, basically this segment of this block diagram and trying to understand what is G1 of S. G1 of S is a transfer function, and it maps the output and the input. So the input to this transfer function is E, output is I or U, depending on what you want to call this. And then the consolidation of this transfer function would be Kp plus Kd S. Okay. So the main benefit of derivative control is it adds virtual damping, and we'll talk about why this is in 1 second here. So if we have D term adds virtual damping. Okay, and so before we said that proportional gains have some favorable properties to them, right? They decrease the rise time, they make the system more responsive or jumpy, right? Faster systems, they make the output get closer to the desired output, and then also the negative effect of they have really high overshoots, or can cause really high overshoots, and so we want to damp out those overshoots, and so what this is going to do is provide virtual damping to our system. So damping, we're not changing anything in our physical system here, but we are changing how the entire system responds by virtually adding damping into a computer here that's controlling the whole system. All right, so this basically allows us to increase Kp with less deleterious effects. Okay, so the reason for this, going back to our previous notes here, we have that G2 of S was given by this equation. This is going back quite a few weeks now, probably 2 or 3 weeks. Right, so this was our transfer function from a while ago here. We now have G1 of S, which we just said, is equal to this transfer function here. And so now if we want to understand what is C over R, our closed loop, so G1, G2 over 1 plus G1, G2. All right, so just inserting these transfer functions in the right spot. Okay, so this would be just adding these transfer functions in, and then we've multiplied, if we want to simplify this, we multiply top and bottom by ms squared plus bs plus k. And this gives us the total transfer function. Got the math up front. And then if we want to get this somewhat similar to second order underdamped form, it's not perfectly there. We can divide by m. Okay, to give us this transfer function. Okay, so question for the class. What terms, we have an s squared term, we have an s term, and we have an s to the 0 term in the denominator, right? So where does damping usually reside? S term, right? Okay, so what has happened? So before, if we go back to your notes from a few weeks ago, the term here, let me clean up that notation just a little bit. It's a little sloppy. Make this very clear. That improved about 10%. Okay. Okay, so if we go back to previous lectures, we would have, if you go back to your previous notes, you would have seen that the term on the S here was B over F, right? So this is B, is the damping that's natural to the system, right? So for instance, my system up front, if I were to, we'll talk about the whole mechanism here in a second, but we have this mass, and if I were to take it from its neutral position, it'll vibrate back and forth, and eventually it slows down, right? So it has damping in the system, right? If it didn't have damping, it wouldn't slow down, right? But we expect something like this to slow down eventually. So the system naturally has damping in it, and that's reflected in this term right here. KF we can't change. That's part of the amplifier and motor system. But we can change in a virtual environment just by changing a few lines of code. We can't change PD, right? So the term that normally determines damping is the S term, right? We now have the ability to, and virtual damping, to augment what was just natural damping in the system. And so that's the main benefit. We'll talk about other benefits too in terms of stability. Damped systems are usually very stable, but that's the main benefit. That's why the derivative term helps here, right? Because it adds virtual damping to the system. So this adds here. And I realized I wrote all this in the wrong spot. And that's why I was running out of room. Crop. All right, that worked amazingly well. Okay. Okay, so this adds virtual damping to the system. Note that we have added a 0 to the system as well. So before, if you go back to your notes, we didn't have a 0. All right, so this is an unavoidable effect of adding a derivative control term. You will add a 0 to your system. Okay, and so then from this we can start to understand some basic properties of this. But I wanted to pause right here and see if there's any questions about adding this derivative term and some of the main effects of it. Yes, Carson. You can make them negative. It's perfectly allowable. Usually not, though. Okay, so the reason for that is because we are using negative feedback. Right, so if we look at the error signal, right, error signal is R minus C. So if that's a positive number, that means that the reference is farther away, is basically a larger number than our actual measurement. So we want to put more input into the system, right? And so by putting a negative gain, it's actually going the opposite direction. Right? So you can have negative gains. That's perfectly allowable. It's not usually a wise design choice. All right, so trying to understand some properties of this. This is going to add virtual damping to our system. It's also interesting to look at what happens in terms of one of the other more unfavorable aspects of proportional control is you have to increase your gain Kp to infinity for the final C final to go to A. So we can take a look at this and see if this helps anything here. So we said that this is our transfer function for C over R. We can apply the final value theorem to this equation. Okay, so assuming that you've built a controller that is stable, which we're always going to be doing first, make sure it's stable, we can look at the limit of time going to infinity of C of t equals limit s to 0, s C of s, right? And so if we're saying this is the step response, we know the form of R, that's A over S. Okay, and then just putting in this transfer function in this location. All right, so this would be our transfer function, or Laplace transform expression. All right, so then we have this s in the numerator cancels this s in the denominator. We evaluate this function at s is equal to 0, and we get that C final is equal to Kp Kf over K plus Kp Kf A. All right, So going back to, yes?
How do we know that our step inputs A or S?
So this is just the generic step input. So we're saying that, so a unit step A would be 1, right? So we're saying that we want our positioning system to go from a position of 0 to 1, and this just parameterizes it, so now we can make it, instead of 1, we can make it 5 or 10 or whatever you want it to be. So just selected that way. Okay, so if you go back a few weeks, so when we were talking about proportional control, you would have seen that C final was exactly the same as this. Okay, so this does not improve steady state response. Okay, so derivative control, it helps with the transient response, right? So if you have a system before that used to oscillate wildly, you can add derivative control to it, and it's going to cause it to damp out those oscillations more quickly and less violently, but it's not going to actually help you when you get to steady state. And so that makes sense too, because if you look at what it's actually doing, it makes sense for a few reasons. It's acting on the derivative of the error. And so at steady state, your system response, all the oscillations have died out, right? So your derivative of your error with respect to time should be equal to 0. So regardless of what KD is, the actual influence in I has no effect. KP is one that affects steady state. And also, for those of you who were here at the Friday before spring break, we talked a lot about the relationships between steady state response and system type. And so you'll see that we have not increased the system type at all here. All right, so if we look at the system type of G1, G2, all right, we have not added a pole to the system, we've only added a 0. So the system type is the number of poles at the origin of the system. So we haven't influenced it at all, so we would not expect it to influence steady state error at all. Okay, the notes go through some of the more, I guess, detailed aspects of this. Basically, it follows that because we have not influenced the S to the 0 term, this is where the natural frequency resides in the system. The natural frequency is not going to be affected, right? So the natural frequency is this S to the 0 term, the square root of S to the 0 term, right? This is not a function of KD at all. So we should not see an effect on the natural frequency. We have added a 0 to the system, so that does have some influences from, as we've talked about before, but some general rules for proportional derivative control are as follows here, is that if we increase KD, C final is not going to change at all. And so this is indifference. Overshoot is going to go down. This is good. This is the most important thing. So it will make the system more aggressive, and one thing you can see is it makes it more aggressive in a certain sense. It adds a 0 to your system, so this will have some effects in terms of decreasing the damp natural frequency, somewhat indifferent there, but also increasing the rise time slightly, decreasing the rise time slightly, and decreasing peak time slightly. And then another thing in terms of what comes with adding damping to the system is we decrease the settling time. This would be second most important. Yes? Because that's not usually a specification we care about. So that's basically, so quick doodle here. All right, so second order response. All right, so this is a function of so it's basically how fast the oscillations happen, right? Not too much of a concern of ours usually. Usually we care about how fast these oscillations settle out, how fast it rises to the next new steady state position. Not usually something people care about all that much. Yes?
What's the problem with raising the derivative term too high?
There are some negative influences. So those of you who have actually implemented PID control on a system before, you may notice that if you increase it too high, you can accentuate noise in your system. And so, just kind of a side on that, we have sensors. We'll talk about sensors on this in a second here. But we have sensors on the system that are then sampled, and also all sensors are noisy. And these are pretty clean because they're encoders in those really clean sensors. But there are some sensors like temperature measurements, etc., that are really noisy signals. And if you just apply a really strong derivative to that case without any filtering, it can be a really, I guess we'll say, bad thing. So just another doodle, I guess, to follow on that. All right, so say for instance, I have some sort of signal and it's noisy. So that means it's like something like that, right? You've seen everyone here from their measurements class or from other freshman engineering has seen noisy signals before, right? So the derivative, what it's doing is it's looking at essentially what is the slope of this line at every time step, right? And the noise, if you look at the slope, if I were to like draw a line saying like what's the slope of this section here, it's like that, right? It's pretty steep. And so if I put a large gain on that, that could have some really negative effects in terms of propagating noise then into my input signal. And so there are ways to handle this. And so there was a question in the forum of, because in this week's homework you have a problem where you're just manipulating the KP, KI, KD gains on your system and observing responses. And there's a question, okay, in Simulink, why is there this extra N term? And you'll see it when you get to it in the PID block. And what MATLAB and Simulink is doing is they're actually using a filtered derivative. And so it has an extra parameter. We'll talk about basically what a filtered derivative looks like later, but they're basically filtering the signal and taking the derivative of it, and they're making the cutoff of that filter so high that it doesn't really affect the main response, but it cuts out noise. Okay, so there are many ways around that problem, but if you just apply a really strong derivative without a filter, it could cause problems. All right, so you may look at this, right? You look at all these mappings, you say, okay, we've handled some of the rise time issues, we've handled the settling time issue, we've settled the overshoot issue. The one thing that we really haven't satisfied yet is how do we get C final to be equal to our actual value we want, right? And so, lo and behold, we have an answer. All right, so this is the purpose of integral control. All right, so integral control, same idea as before. If we compare this to proportional control, this is our standard proportional controller. All right, so this would be standard proportional controller, and I think everyone can guess what's going to happen next. But now we're going to have a Ki gain. We're going to have an integral. And then this is going to be added in. And so this entire box now that's G1. Okay, so going back to this idea of what does I look like in the time domain? Kp E of t, that's the normal proportional controller, plus we are now adding Ki integral E of t dt, and this is integrating from all time, right? So as soon as you click start on your system, it's going to be continually integrating this error. Okay, in the frequency domain, this means that G1 of S, Kp plus Ki over S. And so then if we want to come up, same thing as before when we analyzed proportional derivative control, if we want to analyze now C over R, it's now Kp plus Ki over S. My plant transfer function. Okay, and then simplifying this. So multiplying top and bottom by ms squared plus bs plus k like we did in the last example. Actually, sorry, we're multiplying by something slightly different. S ms squared plus bs plus k. Okay, so numerator, see that we've added a 0 compared to proportional. And now, instead of a second order system like we always had before, we have a third order system. Okay, so no longer, just like with the proportional derivative, that was not a pure second order underdamped system. Same with this case, not a pure second order underdamped system. We have an extra 0, we have an extra pole, which has influences. Okay, so the main benefit of this is improving the steady state performance. So we can analyze this by using the final value theorem, just like we did with proportional derivative control. Okay, so we'll be analyzing, yes?
So as far as how this would actually work, you're going to integrate the error signal. You have to do that, like, if you started that as soon as you turned on your system, and then you just left that continuously, I guess that would, at some point, when that go to, like, infinity, probably, just keep rising. So if you have, like, a buffer of it, or, so you only take it for, like, so many time steps before, how does that work?
Yeah, so I think what you are hitting on here is one of the most dangerous parts about iterative control. Is that, so what you're saying here, just so everyone's on the same page here, another Another doodle here. So you're saying that if you have some sort of system, right, where for whatever reason the error signal is just held for some reason, right? So say here is R of t, and you're holding then C of t just never reaches this for whatever reason, right? And now your error signal is R minus C, right? Which this is the error signal, right? And so you're saying if we were to integrate this, right, the integral of this is this function, right? This integral of v, right? And so you're saying, okay, there's going to be a single term in here that's going to continue to build and build and build, right? Okay. So yeah, this is what's called integral windup. And it's one of the more dangerous parts about integral control. And so you see this, you were explaining the situation where for some reason the actuator was like turned off, right? It wasn't able to, you're saying you turn on the system and then nothing moved, right? And now this error term is integrating or winding up. So that could definitely happen. The most common case where you see this is, like, say for instance, I had like my system and I wanted to spin, 90 degrees, but there was some sort of feature on this and it ran into like a wall, like a mechanical stop that's stronger than the motors on the system, right? So that's the more common case where you see that phenomenon where your actual output never gets to the desired output and you continue to integrate this error, right? Now you have a ton of energy stored in that term, and then when when you finally, let's say, move the reference signal back to where it actually can move, that is going to cause really bad negative effects. Agreed. So there are ways around that. It's called anti-windup control. It's not something that we're going to talk about in this class, but you talk about a buffer, right? So there are ways to handle this where you're continually subtracting out that integrated error if you observe that you run into some sort of wall or something like that. So people figured out that problem too, somewhat, but yeah, that's a big problem with integral control. We'll talk about some of the more basic. That's like a really more complicated problem with it. We'll talk about some of the more basic problems with it, and the fact that we are adding a zero or a pole to the system. Anytime you add a pole to the system, you're actually making the system a little more easy to go unstable. So it can have negative effects on the stability besides the point you just described as well. Okay. So yeah, so definitely some negative effects. The main benefit here is if we look at this in terms of C final, right? We want C final to be equal to A. So if we evaluate this Laplace transform now with the final value theorem, this S would cancel out. Everywhere we see an S, we call that a 0, right? And now we are going to get KF, KI over KF, KI, A, which is equal to A. All right. So now this is steady state. So it doesn't say how long it takes you to get there, but it tells you that the system will eventually get to the value you want it to get to. Okay, so some general rules. If I increase KI, C final will go to A. Good. Sorry, one thing I forgot to mention here. So this is tying this all into the lecture on Friday before spring break where we talked about system type. So if I were to look at, another way I could write this is I get everything under a common denominator here, common denominator of S. This is then KP S plus KI. Okay, so what we're doing when we're adding an integral term is we're increasing the system type by 1. So if our system was naturally a type 0, it's now type 1. If it was naturally type 1, it's now type 2. And so going back to the notes from the Friday before spring break, we saw that as we increase system type, we do better in terms of steady state error in our system, right? So we've incremented or increased the system type. So before where we had a system type 0, and that we had no free integrators in our plant. We now have in a combined system that's system type 1. And we would expect that the error to a steady state error to a step reference to be 0 from what we talked about Friday before spring break. And then here's just another way of showing that. So this is the good major effect of why people put integral control in a system. There are some negative things. So your overshoot will go up. That's a bad thing. Damn natural frequency, no real effect. Rise time, you're making your system more aggressive. This can be, it really depends. Like this is kind of, the notes say it goes down, but that's taken from a textbook. I don't know if I necessarily agree with it. It's very dependent on the system. The biggest thing too is this can cause really long settling times. If you don't do this correctly, this is considered to be a bad thing. Okay. All right, the other thing that this can have a really positive or a beneficial influence on is what somebody called disturbances. So I brought in this cool toy here, and we've run out of time, so I'll have to lug this stupid thing back on Wednesday. Set it up again. But another thing that's really beneficial with is disturbances. Okay, so say for instance, I were to tell the system go from point 0 to point A, say it's like a robotic system in some sort of factory, go from position A, or 0 to A, and I move it here, and then something comes along and it like held in this position, and then something comes along and starts to put a force on it, right? So you can imagine what this could potentially be. This could be some sort of external force. This could be something that you have competing torques in some sort of system that's causing what's called a disturbance into the system. This can also, you can run into kind of, we'll say, soft things that you can eventually just crush and move out of the way. And that would be another dangerous thing about integral control is that it's going to continue to build energy. So a soft thing like people's hands and stuff, that just continue to build energy and crush those things. But it does, and we'll show this. I'll kind of like hold this in the position. You'll see how it'll continue to fight my hand when I put some sort of external torque on it, continue to build energy in the system. So it does, say for instance, if we were to pick up a mass with my mass spring damper system, and it's going against the direction of motion, it can then counteract this mass. So it gives us some robustness so that it can counteract some sort of mass, of unknown mass, some sort of random mass we put on this. It'll build up energy in the integral term to then compensate for that as well. So this is what we call disturbance to our system. We won't talk about disturbances too much in this class, but disturbance is usually anything that is basically something that kicks the system off its normal operating routine, and it's unknown usually. So we're saying we're picking up a mass of some unknown weight, and this will be able to reject that in terms of be able to pick up that weight and get to the steady state value, regardless of what that weight is, within some sort of reason. All right, and then proportional integral derivative. So as you can imagine, this is just all three of them. So we have our proportional controller, and then we have derivative control. all going to 1. So now this is our G1. So if we look at then what is the input as a function of the error, it is the proportional gain times the error plus then the integral term times the integral of the error plus then derivative. And then in the frequency domain, that means that G1 of S is equal to Kp plus Ki 1 over S plus Kd S. Or we can write this all over a single denominator. Like this. Okay, so again, because we have a integral term, what this does is it increases the system type by 1, right? So now we have a pole at the origin in our controller. Okay, the last minute of class. Any questions about this kind of quick overview of PID? And so the last kind of comment on this is that proper design is kind of a balance between all of these. We'll talk on Wednesday's class. We'll kind of ad hoc move around these gains. We'll watch. We'll observe what's happening. The problem statement for the homework, I think it's problem 1, has you do the same thing in Simulink. It's just basically do some work, make some observations, see what happened when you change the different gains. And there's also some theoretical work which maps pretty closely to what we did today as well. But that's the main idea, is that we're going to be looking at the balance between all these different factors, right? So proper design, you have to balance all of these to get good thought. Yes.
So I worked very little with PID.
Yeah.
I worked on hydraulic systems. As a general rule of thumb, at a high proportional term, immediate integral term, and a pretty low derivative term, would that be like the same for these case scenarios, or is it like?
Yeah. So usually a proportional term, then you have integral term, which is somewhere around between 50% to 100% of the proportional term, and then the derivative term is usually about 10% of the proportional term. Yeah, that's a general rule. That doesn't hold, obviously, on every system. Okay, so some systems that just have a lot of damping in them, there's some that have very little damping in the systems naturally. So that adjusts the derivative term. But yeah, that's a really good starting point.
Okay. My question, I guess, on that is, it almost seems like off these notes that you want your integral term to be really low, just because we're only using that to get to steady state value, while our derivative term is more damping on our system. So it almost seems like you want a higher derivative term and like a medium or a lower integral term.
So the integrals, keep in mind the units on all these are different too. So the magnitude of the term is a little bit fictitious. So if we go back here, right, if I is in current, right, so it depends on what your input is. I is in current, that an error would be, in this case, like meters, right? That means that the units on Kp has to be amps per meter, right? If we do error, integral of error, right, that's E dt, right? So this means this is meters seconds, right? So it means the Ki has to be amps per meter second, right? So all the units are different, and so when we talk about gain values, it has to be within that context as well, too. All the units are different. Yeah. So it's a little bit, I guess, we'll say dangerous to talk about magnitudes, but as long as you keep consistent units, then it's a general rule of thumb. It's about 50% to 100% of the proportional gain, the integral gain is. Okay, I've gone over. We'll show this thing on Wednesday then, first thing.